Big data.
Big data.
The big data.
Big data. The big data.
Today's big data.
Let me introduce our first keynote speaker today, Danny McGuirk. Danny is going to highlight the key technical and market trends driving the semiconductor industry today. What amazes me most about Danny is that he served for 24 years in the United States Air Force. For the rest of his background, he is going to tell you himself. So welcome, Danny.
No, thank you. See if I can find everything up here so that I stay on my script. Well, thank you very much and good afternoon, or I should say shay shay and ni hao. Unfortunately, that's 2 of the 10 words I know in Chinese, okay? So I may say one more later on, but that's all I know. First of all, I'd like to thank the CASPA chairman and president, Dr. Liang Peng, for the invitation to be here this afternoon. SEMI has enjoyed a rewarding and worthwhile collaborative relationship for many years with CASPA, and it's certainly a pleasure to be invited here to speak at the Spring Symposium. We have complementary mission statements, CASPA and SEMI, and we have cooperated on a variety of projects in the past, and we hope to do so for many years in the future, so thank you for your support. It's an honor to join this distinguished group of speakers that you're going to hear from. This year's theme, as we talked about, was small silicon, big data. It connects the incredible complexity of IC scaling technology with the massive opportunities that we have in digitization, storage, and analysis of vast amounts of information. The concept of big data often refers to very large and complex data sets, up to the exabyte. And I finally learned what exabyte is, a billion if you want to add all the zeros up for that. It's a big challenge. It also refers to the growing amount of data that is gathered by the proliferation of information sensing mobile devices, cameras, other RFID devices, and wireless sensor networks, and I know some of our other keynotes here will speak to that today. I was asked to speak about industry trends. I'll certainly be glad to do that. And I thought that in addition to looking at SEMI's market outlook, I would like to focus on the innovation imperative, how it originated, and why it's essential for our continued success. In this talk, I'd like to review a few of the most pressing trends and developments facing the nanoelectric supply chain. But first, I have to ask myself, why me? Okay, why was I invited to be here as a keynote speaker? I'm not employed by Lam or Applied Materials. I haven't worked in the semiconductor industry. I don't have a PhD in electrical engineering. But I thought that there's a number of reasons I think I'm uniquely qualified to be a keynote speaker at this event. Number one, I was born in 1947. The year the transistor was invented. I don't think that's a coincidence, okay? How many here were born in 1947? Okay. I got a couple. Okay, I guess I'm not that unique. All right, I was in college, probably the same gentleman will answer. Moore's Law, Moore's observation came along. I started college. I assume the 2 of you were probably starting or in college at that time. In 1969, I graduated from college when the Apollo moon landing, July of 1969. Who here was not yet born by July of 1969? Yeah, there's a few of you. You have no idea what I'm talking about. Then, in 1971, as I said, I spent 24 years in the Air Force flying B-52s. That is a picture of a B-52 for those of you who don't know it. In 1971, I took my first trans-Pacific flight from California over to a little island called Guam, which was 7 hours, a couple of refuelings along the way, 15 hours. There are very few transistors on a B-52 at that time. Okay, so it was radar navigation. For those of you familiar with radar, it doesn't work well over water. You don't see anything. It looks like a big blank space. So what we did was we used celestial navigation, and that's my next question. How many in this room have ever used a sextant in a B-52? Anybody? No? Okay. All right. That's another unique qualification to speak here today. I spent a number of years over in the Southeast Asia area, and the way we communicated was not iPhone, was not text message, it wasn't Skype, it wasn't Facebook. It was Mars. That's not a planet. It was the military auxiliary radio system. Very similar to a ham radio, an amateur radio where you talk to somebody and say, over, and then you wait for the response back. So that was the way we communicated. And the other form was that, it's out of date now, it's called a letter, where you actually wrote something down and put it in the mail, and it was, 2 weeks later you would get the answer back from the letter that you sent home. The rest of my time I spent as an instructor at the Air Force Academy, and that's really where I first came into contact with mainframe computers. Okay, all this time in the Air Force we were probably working on analog stuff, and we had no real computers that we were working with. We did have some when I went to school there between 65 and 69, but that's when you had your deck of cards. For those of you who were around, and you hope when you made it over to the lab, you didn't drop your cards and get them out of order, or they weren't mispunched and you have to start the project all over. I hate to have about 400 cards in a stack and then drop them out in the wind in Colorado, and then you'd have to start all over again. So that was my introduction to computers. I became an avid fan of Atari and Space Invaders. That really qualifies me to speak here because there's probably not everyone here, well, there's some probably didn't play that. I graduated and spent a lot of time overseas. Again, came back and we had a workstation in our office. Okay, it was a big thing at that time. You all gathered around, take a look at the workstation. Pac-Man came around, Apple computers came around, bought my first Apple IIe, got the kids involved in it. Remember what a kilobyte is? Okay, you had a kilobyte, you had the disk you had to put in, you had the floppies, you had all that kind of stuff. And in that time frame, then CNN and ESPN came along, so that you could then have 24 hours, 7 days a week, and sports and news. And that was about 1980. I went then to the Pentagon, where I became more familiar with the technology that was being utilized in military aircraft. I was on a project that was called the F-17. Well, it wasn't called the F-17 at that time. We just called it the stealth fighter. Okay, no one knew what it was. But by 1988, the U.S. government finally acknowledged the existence of the stealth fighter. It had been operational since 1983, and we had 60 airplanes flying around in the Nevada, California area, if you have any idea where things were at that time. And then we monitored the progress of that program by the killer application at the time, and that was Lotus 123, a very, very, very good spreadsheet that we were using. Following that, I went off. I continued to work on a little bit more on the laser-guided bombs, the global positioning satellite for a number of aircraft. So again, became a little bit more familiar with the technology at the time. I left there and retired in 1993, and those are all the acronyms of organizations I was working with, or the head of. The first one, some of you may have heard of the National Rifle Association. They seem to be getting a lot of press lately. I worked for them for a while. I worked for NFPA, National Fluid Power Association, hydraulics and pneumatics. Then I went on to IPC. IPC stood for the Institute of Printed Circuits. It had to do with printed circuit board and electronics assembly, the makers of printed circuit boards, and companies around here. I was talking to somebody, the Flextronics, the Sanmina, the Foxconns of the world. So was involved in that for about 12 years. And I took over at Semi with no background, as I said, no PhD in EE. My son has one, so if I ever really need questions, I can go to my son. And I always have questions. I can always provide me an answer. But I am not an expert in the technology, but I certainly understand the industry and certainly have been involved in it. So as we go forward here this afternoon, what I want to talk about, I'll tell you a little bit about Semi for those of you who aren't aware of who we are. Talk about some of the industry milestones that have taken place over the course of many, many years. Take a look at Semi's market outlook. And then talk about some trends and some challenges that we have in the industry today. and certainly it's going to be for the foreseeable future. Okay, Semi. We're a global organization, very similar to CASPA. We've been around for about 40 years, primarily in semiconductors, but lately in photovoltaics, LEDs, MEMS, and a variety of other different industries. We have about 2,000 member companies. Unlike CASPA, we only have equipment materials, equipment makers, and material suppliers who are members. So they're companies. Many of the companies, obviously, that are here in Silicon Valley that I've already mentioned. Many of you know us for our Semicon shows. Thank you for the advertisement for Semicon China. I'll probably see a number of you over there in Semicon China, and for those of you I don't see, I hope to see you in July for Semicon West, which takes place in San Francisco in the beginning of July. In addition to our expositions, we're also well known for our standards, not just for semiconductors, but for the other industries as well. We also participate in public policy, market research, environmental health and safety guidelines, and other member services that would be unique to SEMI. We do have offices around the globe. I was talking to somebody earlier. We have offices, obviously, here in Silicon Valley and also over in Washington, D.C. But we're also in China, India, South Korea, Japan, Russia, Taiwan, Europe. If I missed one, I'm sorry. But we represent the equipment manufacturers and the material suppliers. Now, what I would like to do is talk a little bit about discovery, invention, and innovation. And here's that's not me in the photo, just so you know. So I want to make some simple distinctions to characterize the differences between discovery, invention, and innovation. Now, when we talk about a discovery, what I'll be referring to, it's a scientific breakthrough that may or may not yield an invention. In the early material science days, we had a number of critical discoveries were made about the nature of semiconductors. And back at Bell Labs in the 1940s, John Bardeen completed experiments that showed how a current applied to a slightly impure slice of germanium could be made to work as an amplifier. He said it was an important observation. It was a discovery. It was supported by a variety of different experiments, but nothing tangible had been produced. So it was an observation or a discovery. Next, we have an invention. And that usually involves the application of a scientific principle to a discovery in some novel or unique way. And it was William Shockley who did that in 1947 when he invented the transistor. And last, it's innovation. And innovation is different from both of these. The term dates back to 16th century England, were really applied to a philosophical, a religious, or a social phenomenon. It wasn't until the 20th century that it applied to technology and industry. And then today, innovation is most often characterized as the lengthy and wholesale transformation of an idea, an observation, into a technology product or process that's meant for worldwide use, or widespread use. So discoveries enable inventions, and inventions enable innovations. And all scientific discoveries don't lead to engineered inventions. And the great majority of inventions don't lead to any innovative process. Innovation requires something more than just the scientific or engineering brilliance in ideas and innovations. The CASPA Symposium is a great setting to discuss the relationship between ideas and innovation. CASPA brings together the semiconductor professionals, academics, investment professionals, and innovators from across our industry. CASPA and SEMI members know that ideas, by definition, can arise from a single individual or a group of individuals. We know that many ideas and inventions can arise nearly simultaneously in different parts of the world as developers seek to apply the latest scientific discoveries. Innovation, on the other hand, requires a whole new set of requirements and resources. The new frontiers in chip making present enormous challenges of discovery and innovation. Only by pooling the basic and applied research from many companies and institutions can discoveries and inventions occur that will enable innovation in the semiconductor industry. Innovation also requires scientific research and discovery to be widely deployed. Semiconductor innovation is judged by its contribution to cost and performance achievements used in the amazing new devices that we have in cell phones and tablets, etc. Deployment can only be achieved by widespread collaboration between foundries and IDMs and between the equipment manufacturers and material suppliers. Now, as we go through a brief history of the semiconductor history, it's a history of collaboration. It was not by accident that the birth of the semiconductor industry began with the AT&T Bell Labs in New Jersey. At that time, the Bell system was described as, quote, the largest aggregation of capital that has ever been controlled by a single private company in the history of the world. Its research arm, Bell Labs, was perhaps the only institution in the world that could staff highly qualified specialists in the multiple disciplines that were necessary to give birth to the transistor, the laser, and the other critical inventions of the information age. Today, the monopolies with the scale and the scope to fund R&D to sustain semiconductor advances no longer exist. Research consortia and academic institutions and public-private research initiatives are necessary to support the critical research needed for semiconductor innovation. R&D is also distributed throughout the supply chain. In the early days, even the monopoly AT&T knew it did not have the required staff or the resources to fully exploit the invention of the transistor. In comparison to the then vacuum tube, that's what we had on B-52s, by the way, primarily, the transistor was still very expensive. For the first years of existence, only military contracts could sustain its development. When the transistor first came out, the customer was primarily the military, and that was, the race to the moon. A project that was that I worked on was called the Intercontinental Ballistic Missile. Many of those, the transistors were involved in the production of those systems from the Air Force. Now, many of you recognize this. I even recognize this. Moore's Law. Since its invention, the transistor and its silicon-based offspring would continue to be refined and improved at such a steady pace that Gordon Moore observed that the number of transistors that could be placed on an integrated circuit would double about every 2 years. Moore's Law describes the underlying force that has driven technological change in our industry for about 50 years. All of today's consumer electronics, our automobiles, space exploration, health, medical, they've been made possible by the continuing improvement in cost and performance in the computing power described by Moore's Law. Now, Moore's Law wasn't a discovery, it was a historical observation, as Gordon Moore suggested. The reason it has existed and proved accurate for nearly 50 years is because hundreds of companies and thousands of people, like many of you here in this auditorium this afternoon, have agreed to make it possible. It's an industry-wide agreement for continuous improvement at an agreed-upon rate. And Gordon Moore himself said it was a self-fulfilling prophecy when he first published it in the Electronics magazine back in 1965. In the beginning, when the industry was small, Moore's Law occurred nearly simultaneously in different companies. Later, Moore's Law took place around industry roadmaps that defined in a very precise fashion what needed to happen throughout the supply chain to continue the pace of cost reduction. For several years, the roadmap was called the National Technology Roadmap for Semiconductors. And then in 1998, it became more of a global effort and involved hundreds of companies worldwide, and the name was changed and it became the International Technology Roadmap for Semiconductors. And some of you may know that as the ITRS. Now, in addition to the roadmaps, as I described, the semiconductor industry also agreed upon collective industry standards to reduce costs and to spur innovation in our industry. The standards involve areas such as the wafer size and dimensions, software, hardware interface, materials characterization and test methods, and hundreds of other areas. Today, we have nearly 4,000 volunteers from every major company, and again, some of you here in this room, working on industry standards. They have produced hundreds of widely accepted standards that have reduced costs and allowed companies to compete on innovation. The semiconductor industry is built on both roadmaps and standards. Standards agreed to by all device makers and the suppliers. In fact, standards and roadmaps have gone together since we first had a roadmap and we first started developing standards. Technology roadmaps define where companies can compete. Standards define where companies can productively collaborate. Now, SEMI has been involved in international standards. We have approximately 800 of them, and they guide manufacturers, equipment, and technology and material suppliers in their pursuit of Moore's Law. The importance of standards can be illustrated by today's modern chip manufacturing process. Many of you are certainly more familiar with this than I. Leading-edge semiconductors require more than 700 process steps in the manufacturing operation. Over 100 different suppliers may be required. And in the materials area, what once required perhaps 7 elements on the periodic table now require over 30 elements, many of them in a variety of different formulations. Many of these equipment types and material sets change every 18 to 24 months to keep up with the dictates necessitated by the next node. All of these suppliers are competing. They're all engaged in independent, advanced, high-test R&D to meet their customers' needs. All of them are also collaborating by contributing to and using industry standards so their latest projects can be quickly and seamlessly integrated into the next node on the manufacturing line. Without effective standards, the blue screen of death is going to show up. The whole system crashes, equipment won't integrate, material sets and test methods will proliferate, and process R&D wouldn't translate into production. Without standards, the enormous R&D necessary to keep pace with Moore's Law was very similar to the square peg, trying to get that into the round hole. It's just not going to work. Now, standards are well known to be valuable in reducing costs in the manufacturing process, and manufacturers begin a formal process to investigate how these costs can be reduced. I want to go through this because I see I only have a couple more minutes left here, and I want to get into some of the challenges. So let me get into this evolution of the chip demand. We can talk about, and I talked about very briefly, how we've gone from a general purpose computer up to the ubiquitous surrounding of devices. Devices everywhere. Everywhere we go, we have devices. The cycles for the semiconductor, very briefly, you can see that we're expecting a fairly single-digit growth over the next few years. And by 2015, we're going to go about $300 billion a year for semiconductors, up to $330 billion. These are the chip industry growth segments that we anticipate in the growth areas, and you can see that some of them are over 25 and up to 50% growth in 2013. And the overall IC market is expected to grow about 6% for the year. Very quickly, we talk about Moore's Law and more than more, and these are some of the challenges that are facing those of you who are working in the industry. One of the big challenges that we all have are different device structures, and the FinFET has come around. Intel certainly has started that, and that is a device structure and a piece of architecture that is certainly helping in the industry. A big challenge here is lithography. Many of you are aware of ASML, and we've had some problems with trying to put together the EUV. There's a picture of me on the lower right-hand side. I'm standing this is up at Albany at CNSC with the G450 consortia, and that behind me is the R&D version of a tool that costs about $60 million. The big tool up on top is a production model. It'll probably cost between 90 and 100 million dollars. Right now, ASML, the concern is the power source. So they purchased a company called Cymer down in San Diego. Many other companies have been concerned about the progress not only of EUV, but of 450. Intel, TSMC, and Samsung all have invested in ASML to certainly help this along. I'm not going to talk too much about the packaging, but 3D IC certainly continues to be a major challenge as we go forward. Certainly one of the major areas, the transition to 450 millimeter, is going to continue to be a concern and a challenge as we go forward. As you can see, we've transitioned to various wafer sizes over the course of the years. 450 is a big step. 450 is a big step because there's a limited number of IC makers who are going to make this transition. That must be my number there, huh? The 450 standards now, we're continuing to work on the standards. We have a variety of them working on. One of the concerns about the transition for 450 is the cost. Anywhere from $8 billion to $30 billion. There are a lot of things that have to operate right if we're going to make that transition by 2016, 17, 18, whenever that happens to be. In summary, what I'd like to say is, I've rushed through some of this. I apologize for that. I plan to be around here for a while this afternoon. But there are a number of industry challenges that we face, and I know that we're going to talk about these when we talk about small silicon and big data. The history of the industry was one of innovation, and that certainly requires collaboration. And as we go forward, we want to continue working not only with CASPA, but with all of our member companies worldwide. We want to continue to work on collaboration so that we have true innovation, not only here in the Valley, but throughout our industry. Semi will be at the forefront for our members. I want to thank you for inviting me over here this afternoon, and I look forward to getting a chance to see some of you after this is over and working with you sometime in the future. So that concludes my briefing. Sheshe.
Thank you very much, Dennis. Now let's invite Peng Liang, our president, to present this plaque to Danny through the speaker. Thank you very much.